have started your attempts to procure a textbook of heat transfer. So it's always better as a mechanical engineer. Heat transfer book is useful, important, and it will be helpful for you in the future. Also, it's better to have a textbook, and also the design, the heat and mass transfer data book. So, what I have shown you in the previous class, the data book by C.P. Kodanraman. That you need to have it because that will help you in accessing the data, and also you won't have to memorize a lot of equations that you will be dealing with in heat transfer. Okay. So procure these two books, textbook of heat transfer and also the heat and mass transfer data book. Okay, so in the last class we have started the introductory part in the module 1 about the basic modes of heat transfer, conduction, convection, and radiation. Some analogies were explained to you, and some governing equations related to conduction has been shown to you. The equation that governs the heat conducted is called as the Fourier's law of heat transmission, and as I said, it's a law just like the other laws that we'll be seeing in today's class. In today's class, we'll see the law that governs the heat convection and also the heat radiated. So laws are not derived from fundamentals; they are framed based on empirical data and also the experience of people who have worked in that field. Okay, so let me share the slides with you. So in the last class, this is where we have stopped. We have seen the governing equation for heat conduction, Fourier's law of heat conduction. So there is thermal conductivity involved, the surface area available for heat conduction involved, and also the thermal gradient involved. You will see that we will actually use this thermal gradient in the first experiment that you are going to do next week in the lab. The experiment called as the conductivity of a metal rod, that is an experiment which utilizes this thermal gradient dt divided by dx. Okay, so this is something we have seen, and we have also seen the values of conductivities for various materials. Diamond, obviously, it is a non-metal, but it has got extremely high thermal conductivity. But we cannot really use diamond for industrial purposes because of the cost. That is followed by silver, copper, gold, and so on. But again, silver and gold, precious metals, they have other applications, ornamental value, therefore not so much used in industries. But copper and aluminum, and among copper and aluminum is more preferred because again, aluminum is cheaper, and copper is expensive, and also copper is heavy. Because of that, you will see a lot of applications using aluminum as a material having good thermal conductivity. And also there are other materials which have a poor thermal conductivity. Okay. Then we have seen this variation of different conductivities with respect to temperature. The general observation is that for solids and for metals, the conductivity decreases with temperature, whereas for gases, it is increasing with temperature. So in this material, in this slide, we have seen that in a solid, the conductivity is because of two reasons. One is the lattice vibrations, that's the arrangement of the molecules, vibrations about their mean position, and also the flow of free electrons. So these are the two parameters which contribute to the thermal conductivity of solids. So in the last class, one student asked, why is that the thermal conductivity of solids decreases when the temperature is increasing, whereas it's increasing for gases. Because for gases, it is understandable that as the temperature increases, the energy of the molecules increases. They move more randomly. They strike each other more frequently, and therefore the transmission of heat is increasing, thereby contributing to the increasing the thermal conductivity. The same explanation cannot be given to solids, because we can see that solids, some solids, the drop in thermal conductivity is there, but minimal, but for some the drop is extremely large. Now the reason for this is given in two different ways. First one is from the physics. In fact, both the reasons are from the physics viewpoint. One thing is about the anharmonic scattering, something called as a anharmonic scattering, which happens when the temperature increases, and this anharmonic scattering is inversely proportional to the temperature. So when the temperature is increasing, this anharmonic scattering is decreasing, thereby contributing to the drop in the conductivity. Another thing is, another reason that is also given, or people try to explain this drop in the conductivity is because this conductivity is a function of this lattice vibrations and also a flow of free electrons. What is happening at high temperature is that this lattice arrangement is getting distorted. So at low temperatures, there is certain arrangement. At high temperatures, the arrangement is changing, and that change in the arrangement is actually blocking or becoming a hindrance to the flow of electrons. So because of this reduced rate of flow of electrons, there is a drop in the conductivity. That is given in literature, but the overall understanding is that we have no proper understanding of this behavior of thermal conductivity as a function of temperature. So some theories have been proposed, but not completely clear, and so this particular fact is not completely explained. Okay, so that is the answer to your question. We'll come to the next mode of heat transfer, called as the convection. Convection is the mode of energy transfer between solid surface and the adjacent liquid or gas that is in motion. So for a convection to take place, there should be a solid surface, and a fluid adjacent to the solid surface. So that fluid can either be liquid or a gas, and that liquid or a gas must be in motion relative to the solid surface. So that relative motion is sufficient for convective heat transfer to take place. For example, an aircraft moving in aircraft flying in an atmosphere. Aircrafts fly at 30,000 feet, where the atmosphere is quite thin and still, and there is a movement between the solid surface, the wings, the fuselage, the body of the aircraft, and also the ambient atmosphere, the air, and therefore there is a convection involved in that case. But there the air is not moving. Absolute movement of air is not there. It's only moving relative to the body of the aircraft. So the relative motion between the solid surface and the fluid is necessary for convection to take place. It involves the combined effects of conduction and fluid motion. You will see later that, or in fact, you are also familiar by now, there is a phenomenon called as the boundary layer. What is this boundary layer? There is what is called as the velocity boundary layer, and in heat transfer you will also see something called as the thermal boundary layer. This boundary layer is basically a thin film adjacent to the surface where there are variations in properties. When we talk about velocity boundary layer, you will see that there will be variations in the velocity. In the thermal boundary layer, you will see variations in the temperature. So such that thin layer is very much is kind of a stationary layer adjacent to the solid surface, and in that thin surface, some regions in the thin surface, because the fluid is stationary, conduction is more prevalent. Therefore, whenever we talk about convection, conduction also comes into picture to a certain extent. Then there are two types of convections. The one is the forced convection, which takes place when the flow caused by the external means, like a fan or a pump or a blower. So some kind of an external device which drives the fluid to flow over the surface. So that is called as the forced convection. Most industrial applications will have this forced convection, because we want some kind of a positive convective heat transfer. Either heat supply or heat removal. We want that to happen positively. Therefore, we go for forced convection wherever there is no restriction in space. In some cases, we are forced to go for free convection. Free convection is something that takes place due to density differences. So we know that in a fluid, when there are density differences, the high density fluid will try to come down, and the low density fluid will try to rise. So hot air rises, cold air loses altitude. We are familiar with this. So this is because of the density differences, and this density difference is caused by temperature differences. So because of this, there are some buoyancy forces involved in free convection, and therefore, in general, free convection is something that takes place in the absence of an external device. So that's what happens. We go for free convection when we don't have the space or the provision to include a external device like a fan or a pump or a blower or a compressor. Here you see some examples of convection. Here you see this is some kind of an electronic circuit. Let us say this is a printer circuit board, and when you are including a fan here to force air to flow over the surface, you see all these electronic components, they release heat due to the processing. So that heat has to be removed away. Otherwise, if the heat accumulates here, then the temperature of this circuit board, the electronic components will increase, and which is not good for the performance. Therefore, this heat has to be removed. If you put a fan to remove this heat, we call it as a forced convection. So you must have seen in desktop computers, there is a CPU, the big rectangular box, which actually has a fan at the back. So this fan is actually not a forced draft fan, but it's an induced draft fan. That means it kind of sucks the hot air from inside and discharges it to the atmosphere. So that is what we call as the induced draft, but still it is a forced convection. Now, in some cases, we may not have enough space for the air, for the heat to be removed. In such cases, we cannot provide this external device. Providing the external device may not be possible because there is no space, and also it could be expensive, and so on. In such cases, you can see the electronic devices, the orientation has been changed now. You see, this is the orientation, horizontal orientation. Now, in the case of free convection, it has become a vertically oriented. And in this case, the buoyancy, the flow is because of the buoyancy driven flow. What's happening? Air is coming into contact with these hot surfaces, absorbing heat and becoming light and then rising up. So whatever air is evacuated because of this rising up is taken. This region is now occupied by the cold air which is coming in from outside. So in this way, we have this natural circulation setup. So another example of convection is what is called as the boiling. So you can see here there is a pool boiling taking place. Pool boiling is something where we take a fixed quantity of liquid and put it in a pail of put it in a vessel and subject it to heating. After some time it will start boiling. So that is called as the pool boiling, as against convective boiling or flow boiling, where the fluid is continuously flowing and still undergoes boiling. So this example is that of a pool boiling. And you can see here the vapor, as the heating takes place, the vapor bubbles are formed initially on the bottom surface of the vessel. The vapor bubbles form. Initially, the bubbles will be smaller in size. Later, the bubbles will increase in size, and then they start rising. And in the process, bubbles also join together. They rise to the top, and at the top, some bubbles burst. And that is how some convection currents are set up during the boiling process. So we have an experiment in our lab. You will observe all these phenomena. So because of this movement of these vapor bubbles, the phenomena of boiling is also treated as a convection. And the last example is that of a condensation. Condensation takes place whenever a cold object is cold surface or a cold object like a cool drink. If you take out a cool drink from the refrigerator and keep it on the table on a hot, humid day, what happens is there will be droplets of condensation forming on the surface of the cold drink can. These droplets are basically water from the atmosphere, the humidity from the atmosphere, which is condensing because they have now come into contact with a cold surface. So these droplets, they form on the cold surface and then they move down. So initially, you see this here, there is a droplet and it will move down. There is a droplet formed, it will move down. So this movement of these droplets because of gravity is also inducing convection. So whenever there is a fluid movement, convection is involved, and therefore condensation process is also treated as a convection. So you may not be knowing this until this point, but boiling and condensation together are treated as a convective phenomena, and they are studied along with convection. Now, how to evaluate the convected heat transfer? So just like we had the Fourier's law for heat conduction, we also have a law for convection. So that law is called as the Newton's law of cooling. So that law gives the rate equation for convection. So what is that equation? Again, Q is the heat, subscript CONV stands for convection, and there is a dot on top of Q, that is the rate of convection. So this rate of heat convected is equal to HA multiplied by one temperature difference, Ts minus T infinity. So what is this Ts and what is this T infinity? You can see that here, this whatever fluid is flowing, that fluid's temperature is T infinity. And the surface over which the fluid is flowing, that temperature is called as a Ts. So Ts stands for surface temperature, T infinity stands for the fluid temperature, and the rate of heat convected is equal to the difference between the surface and the fluid temperature. So that comes into picture. Apart from that, the area available for heat transfer, that is always there. That is there in conduction, it is there as you see in convection, and it will be there in radiation also. So remember, area available for heat transfer plays a major role in the heat transfer processes. So heat transfer processes are area driven processes, and therefore if you want heat transfer to increase, you should increase the area, and if you want to decrease, you have to decrease the area. That is one option available to achieve what is needed. Apart from that, there is a new term here called as the symbolized as H. H is called as the convective heat transfer coefficient. So you may think that this H is something equivalent to K that we have seen in conduction. Wrong. H is not equivalent to K. The difference between H and K is that K is a material property. So it depends on the material and also some other factors. But H does not depend on the material. H depends on other conditions. For example, it depends on the orientation. It depends on the conditions. For example, in this case of forced convection, the value of H will be high, whereas in the case of this free convection, the value of H will be low. So the same configuration, the same materials, the same heat generation for a chip, when the chip is subjected to this orientation, horizontal orientation and a forced convection, there will be a one value of H, and when the same chip is reoriented vertically, and if you remove the fan, it will have a different H. Therefore, H is not a property of the fluid. It is a parameter which is depending on the orientation and other conditions which we shall see now. So the entire study of convective heat transfer is mostly dedicated to determining this value of H. Because H is not a property, it is not tabulated in a data books. We will have to evaluate, and we will have to evaluate for different situations. So that is the difficulty involved with the heat transfer coefficient H. Because of that, you will see that when we deal with convection, you will see that there are several correlations. What are correlations? Correlations are basically equations, but derived from empirical experience. So not derived from mathematics or not derived from physics, but derived from the experience of the researchers. So you will see that to determine the heat transfer coefficient, there are a lot of correlations. We'll see that later on. So here the point is the convective heat transfer coefficient is not a property of the fluid, and that is important to remember. Now, what are the typical values of the heat transfer coefficient? So you see here, there are the typical values given to us. When the convection is the free convection of gases, remember gases and free convection, then the value of H is in this range 2 to 25. That means if you are trying to cool a cup of coffee by just putting it on the table, then its heat transfer coefficient will be in this range, 2 to 25 watt per meter square Kelvin. So it will take a long time to cool down. If if this is gas, for free convection of liquids, that means if you drop a hot steel plate in a pool of water, then the heat transfer coefficients will be in this range, 10 to 1000 watt per meter square Kelvin. So you see, this is a wide range, 10 to 1000, depending on various conditions. So these ranges are only indicative. There's nothing hard and fast about it. Then forced convection with gases, you can see it is about 25 to 250. So when gases are involved, the heat transfer coefficient increases under forced convection conditions. And also for liquids, forced convection of liquids, the heat transfer coefficient increases now 50 to 20,000. But what is alarmingly or noticeably different is the boiling and condensation. For this case of boiling and condensation, the heat transfer coefficients are about 2,500 to 1 lakh. It is a typical range, but there are situations where the heat transfer coefficient can go beyond 1 lakh. So you can see the larger this number, higher will be the rate of heat transfer coefficient according to this equation. Therefore, boiling and condensation processes are suitable when you want to transfer large amounts of heat. Especially, remember, boiling and condensation, the temperature of the fluid which is undergoing the boiling and condensation will remain constant. Therefore, when you want to transfer large quantities of heat at constant temperatures, the ideal processes will be boiling and condensation. In either boiling or condensation, you see the heat transfer coefficients are extremely large. So another thing which you can notice from this particular table is that gases in general, when our fluid is a gas, in general, the heat transfer coefficient will be poor. So you can see for free convection, gases have lower heat transfer coefficient range than liquids. Similarly, for forced convection conditions, gases have lower heat transfer coefficients than liquids. Okay. So what you can see is that under forced convection conditions, heat transfer coefficients are high, and for gases, always the heat transfer coefficients are lower than liquids. And overall, the boiling and condensation have the very large heat transfer coefficients. Now we can think about some applications here. For example, let us come back to this electrical vehicles. In the electrical vehicles, I have given this example of battery and motors which need to be cooled because of some restrictions in the temperature ranges. Okay. Now, if you want to cool a battery or an electric motor with the help of air, you see, if you have seen an electric motor, you will see that on one end of the electric motor, there will be actually a fan fitted. It draws the air from the outside and cools it down. Now, such an arrangement is good enough and is sufficient for a small motor whose duty is not heavy, so which doesn't generate a lot of heat. But what happens if there is a motor which generates a lot of heat? Then and also that motor is enclosed. Remember, in electric vehicles, you cannot leave the motor open. It has to be protected from the atmospheric conditions, and also you will see that electric motors are having certain protection from water submersion. Remember, electric vehicle motors are meant for automobiles, which in some cases may have to travel underwater for at least a brief period. But during that brief period, you don't want water to go into this motor. So in such cases, we can't have this air cooling. So these are certain restrictions here. So in such cases, when air cooling is not sufficient or when you cannot keep the motor open to the ambient conditions, you will have to rely on other modes of cooling. So there we go for liquid cooling. So we use liquids to cool the motor. Similarly in automobile engines, IC engines, the coolant is something which carries away the heat from the engine jacket. And now the coolant has to be recirculated. So to cool down the coolant to the initial temperature, we pass that through a what we call that radiator, through the radiator. So now here also air cooling of the engine is not sufficient. So we will have to use a liquid having a good thermal conductivity so that it can carry away the heat effectively. So this is these are the typical values, and that's about the convection. Now coming to the radiation. Now radiation is one of the most complicated modes of heat transfer. It is difficult to understand, it is difficult to evaluate. Understanding is difficult because there are many factors involved in radiation. You will see, I will show you the governing equation for radiation. There are many factors involved. And also it is difficult to evaluate radiation because of the nature of the equation. I will show you that also. Now before that, we'll go into some theory about radiation. Thermal radiation is the energy emitted by the matter that is at a non-zero temperature. So any matter, any substance, or any entity that is at a temperature above 0 Kelvin. When I say non-zero, I'm not talking about 0 Celsius. I'm talking about 0 Kelvin. Okay, anything above 0 Kelvin will emit radiation. When it is about 1 Kelvin, it will emit less radiation. When it is about 100 Kelvin, it will emit more radiation. 1000 Kelvin, much more radiation. So higher the temperature, higher the radiation. But nonetheless, if it is just above 0, then it will definitely emit radiation, emit thermal radiation. Now there are several types of radiation. Thermal radiation is different. You know that there is radiation is an entire spectrum, and only a part of that spectrum is thermal radiation. So thermal radiation differs from other radiation like X-rays, gamma rays, and microwaves that are not related to temperature. So you will see that in the entire spectrum of radiation, thermal radiation is only a part. Similarly, there is solar radiation, it's only a part. Likewise, there are X-rays, gamma rays, which are a part of the entire spectrum. So all these things we shall see when we study the radiation heat transfer in the later modules. Thermal radiation can occur from solid surfaces, liquids, and gases. So, all phases of matter can radiate heat. The radiation is attributed to changes in the electron configuration. So, this again is about the physics part of the radiation. Now, here there are two situations shown and how the radiation exchange is taking place. Here there is one surface, a very simple surface which is exchanging heat, radiation exchange at a surface. So there is a surface here. This surface is at a temperature Ts, and also it has got a certain emissivity and certain absorptivity. Now what is this emissivity, what is this absorptivity, we shall see very soon. So you can see that there is a surface, and adjacent to the surface there is some ambient atmosphere. In this case there is a gas which is at a temperature T, and there is a H. H is the heat transfer coefficient associated with the convection. So for this surface, the modes of heat transfer will be, you see, this surface is receiving heat from the surroundings. So this is G, represented by G. This wavy symbols are used, wavy arrow is used to represent the radiation heat radiation. So G is called as the irradiation. It is the radiation received by the surface, and E is the emissivity or emitted radiation by the surface. This emitted radiation is because of the temperature of the surface and also because of the emissivity of the surface. Now, whatever radiation is falling on the surface, this G, part of it is absorbed by the surface depending on the absorptivity factor. Part of it is reflected. If there is, this surface is reflective in nature, part of it is reflected, and the remaining is transmitted. The remaining radiation will pass through the surface. All these things we shall see later on. So here we can see that because of the temperature of the surface and the absorptivity of the surface, there is some radiation emitted by this surface. And also because of the presence of the gas and the temperature difference between the gas and the surface, there is a convected heat. So the total heat transfer between the surface and the surroundings is the radiation heat transfer plus the convection heat transfer. So most times we will have to deal with this combination of the modes of heat transfer. This combination of the modes of heat transfer is called as the conjugate heat transfer. So two different modes of heat transfer are coming to picture, and sometimes there can also be three modes, but that's a rare case. So this is one surface, so one example of radiation exchange at a surface. Now sometimes the same surface can also be enclosed in some kind of a surrounding. For example, there is a hot there's a hot nuclear reactor in a building, inside a building. So that means this hot reactor is a surface and a building forms the surroundings. So in such a case, there will be radiation exchange between the surface and the large surroundings. So large surroundings, because of the temperature, they will be emitting radiation. The surface, because of its temperature, will be emitting radiation. So there is a radiation heat transfer involved. There is a convection involved. There is a convection because of this gas. Okay, so this there is a difference between this orientation and this orientation, and we will see how to evaluate the heat transfer in these two cases. Okay, so these are some typical examples where we can consider radiation into picture. Also, there are situations where radiation comes into picture in combination with the natural convection. You know, we have seen that in natural convection, the heat transfer coefficient is low, because of which the rate of heat convected is low. So in such cases, the amount of heat radiated can also be as good as the amount of heat convected, heat naturally convected. In such cases, we will consider radiation. But in many cases, in most cases, the radiation, when the convective heat transfer coefficient is large and the radiation, the temperature which is responsible for radiation is something less than 500 degrees Celsius, we kind of tend to neglect the radiation heat transfer. Why do we neglect? We shall see later. So here, the rate equation for the radiation heat transfer. So again, as we had rate equations for conduction and convection, we also have one law which determines the rate equation. That is the Stefan-Boltzmann law. The Stefan-Boltzmann law gives the upper limit to the emissive power of a surface at a temperature. So unlike the other two equations, the Stefan-Boltzmann law does not give the heat radiated or net heat radiated, but it gives the maximum emitted radiation for a surface. So that is the difference, and therefore you see you don't see any difference in the temperatures. In conduction heat transfer coefficient, we saw that dT divided by dx, that dT is a difference in temperature. In convection heat transfer coefficient, we saw Ts minus T infinity, that is a difference in temperature. Whereas in case of radiation, this law does not give any difference in temperature. You see, we just see Ts raised to the power 4. Okay, so there is no difference in temperature involved in this case, because it is an equation which tells us what will be the maximum amount of radiation emitted by a surface. So Q is the radiation emitted, Q dot, that means the rate of heat radiated. When we say rate, we are talking about joules per second or kilojoules per second. Therefore, our units of the Q dot will always be watts or kilowatts or megawatts, depending on the quantity. Now, this is the emitted radiation, rate of emitted radiation, and the maximum value. So this is the maximum value for a surface. It cannot exceed this value. So what is that maximum value? It is given as a sigma multiplied by As multiplied by Ts power 4. Sigma is what is called as the Stefan-Boltzmann constant. As is the area of the surface available for heat transfer, and the Ts is the temperature of the surface. But since there is no difference involved, this temperature of the surface is the absolute temperature. So you should be very careful whenever you use this equation in radiation. This temperature must always be in Kelvin. It should not be in Celsius. It should not be in Fahrenheit. It should be in Kelvin. Okay, so this is the equation, and the value of sigma is the Stefan-Boltzmann constant is 5.67 multiplied by 10 power minus 8. The units are watts per meter square Kelvin. Okay, now it's very easy to remember this number 5, 6, 7, 8. So it's an order, sequential order 5, 6, 7, 8, except that there is a decimal point 5.67 and 8 has a minus sign. So 5.67 multiplied by 10 power minus 8 is the value of the Stefan-Boltzmann constant. Anyway, this value will be available in the data book, so you don't have to really memorize this, but it's better to remember because this is a very useful and commonly used number. Now coming to the black body. Black body is a concept introduced in radiation to idealize a surface which can emit the maximum amount of radiation. So an idealized surface which emits the maximum radiation is called as the black body. So the radiation emitted is black body radiation, and the real surfaces which are not black emit less than a black body. Therefore, to modify this equation and to bring about black body, this equation is modified by including one term called as the emissivity. This symbol is called as epsilon. So this emissivity symbol is used to bring about the influence of the blackness of a surface. So black body will have this value equal to 1, whereas real surfaces will have a value less than 1. Therefore, real surfaces emit radiation much less than a black body. So emissivity is a measure of how closely a surface approximates a black body. So black body emissivity is equal to 1 and real surfaces will be less than 1, between 0 and 1. The closer the value is to 1, the blacker the body is. So that's how you can understand this. And now you can see that in this emitted radiation heat, the temperature is actually raised to the power 4. We didn't see this in conduction and in convection. That means this particular equation is a non-linear equation. So that this particular non-linearity makes the study of radiation heat transfer difficult. So because of that, we have this radiation heat exchange defined. So you see this equation, radiation heat exchange can be defined. Let us say there are two bodies. One is at a surface temperature Ts and the surrounding is at a temperature T SURR, T surrounding. So the net radiation exchange between these two will be the same equation. So we write this quantity for the surface and the same quantity for the surroundings. So radiation emitted by the surface minus the radiation emitted by the surroundings will give you this equation. So you can use this equation to find out the net radiation exchanged between the surface and the surroundings. Now you see this equation has got temperatures, absolute temperatures raised to the power 4. So this makes me uncomfortable, this temperature to the raised power 4, because if I have to solve this, if I am given the radiation heat transfer and if I have to find out the value of the surface temperature, I have to evaluate the fourth root of this temperature, which is not that easy. So for that reasons, I want to linearize this equation. I mean, I want to make it less non-linear. So for that, what I do is just like the heat transfer in convection, the Newton's law of cooling, I use a similar equation to quantify the heat radiated also. But now I say instead of H, I say HR. That means heat transfer coefficient in the radiation. So HR multiplied by area multiplied by the temperature difference, temperature of the surface minus the temperature of the surroundings. So what I'm doing is that I'm writing the radiative heat transfer in the form similar to the convective heat transfer. But then these two quantities must be equal. That means this quantity and this quantity must be equal. That means this. So this quantity and quantity must be equal. So I equate these two quantities. So this is the form of equation written on the basis of the convective heat transfer, and this is the form of equation written on the basis of the radiation heat transfer. Now I want to evaluate this value HR. So I take out HR from this equation. So this term will go into the denominator. So we have this term here. Now this Ts power 4 minus T surrounding power 4 is like a square minus b square. We know that a square minus b square can be written as a minus b and a plus b. So I write this as Ts square minus T surrounding square multiplied by Ts square plus T surrounding square. And in the denominator, we have this Ts minus T surrounding, this Ts minus T surrounding as this. So again, we have here Ts square minus T surrounding square. It's again like a square minus b square. So it can be written as a Ts minus T surrounding multiplied by Ts plus T surrounding. Now I have this Ts minus T surrounding in the denominator. So I can cancel this and this. So what's remaining is this term, and this term. So now I have the radiative heat transfer as epsilon sigma Ts plus T surrounding multiplied by Ts square plus T surroundings square. So using this, I can find the radiative heat transfer coefficient. Once I have this radiative heat transfer coefficient, I can use it in this equation to easily evaluate the radiative heat transfer rather than use this equation, because Why? This equation is non-linear and it makes me uncomfortable. So this is one way of making this equation less non-linear. Okay. Now coming to the emissivity. Again, emissivity and absorptivity. Emissivity of a black body is equal to 1, and for real surfaces, emissivity is between 0 and 1. I'll show you a list of emissivity values. Similarly, absorptivity is the fraction of the radiation energy incident on a surface that is absorbed by it. So I've shown you one image here. This is the radiation falling on the surface, but not all of it is absorbed, only a part of it is absorbed. That part of it, that fraction of what is absorbed is called as a absorptivity. So different surfaces will have different amounts of absorptivity. So G absorbed, that means the radiation absorbed is equal to alpha absorptivity multiplied by the irradiation. G is called as the irradiation, that is the radiation falling on a surface. Again, value of absorptivity is something between 0 and 1. So here there are values of emissivity. Emissivity values are very important. Uh, you can see here for aluminum foil it is 0.07. That means aluminum foil, even though if it is hot, it won't emit radiation. Anodized aluminum 0.82. So same material, aluminum foil and anodized aluminum, same material, but depending on their form and nature, anodized aluminum has got high emissivity, whereas aluminum foil has got a low emissivity. Similarly, human skin has got emissivity of 0.95. Water 0.96. That means hot water will actually emit a lot of radiation. Soil 0.93 to 0.96. Okay, so in this way we have different values of emissivity, and this emissivity data is available in data books. Black paint has got a high emissivity 0.98. That means when you paint surface black, it will actually emit a lot of radiation if it is hot. Now we all know that when we order food from this delivery apps like Swiggy, Zomato, and so on, the food is delivered in the form of it's packed in packets and wrapped in aluminum foil. So this is helpful because the food is remaining hot. What happens is aluminum foil, even though if it gets hot because of the conduction from the food, uh, its emissivity is very low. So even though the foil is hot, it won't emit radiation. That means the radiative heat transfer is minimized because of this aluminum foil. Now we all studied first law of thermodynamics, which is related to heat transfer, and also we studied second law of thermodynamics, which involves rejection or receiving heat. So how is this heat transfer subject or heat transfer concept related to the first law of thermodynamics? So the first law deals with the conservation of energy. This is something we know. And first law deals with both closed and open systems. In many cases, we end up estimating the heat to be removed or supplied. So when we solve several problems on first law of thermodynamics, we end up finding out what is the amount of heat to be supplied to produce so much amount of work. So that kind of problems we solved. But how to supply that heat or how to remove that heat, that is not determined by, or that's not told to us by the thermodynamics or the first law of thermodynamics. Similarly, when we come to the second law of thermodynamics, it is this law of the statement. We have two statements here. The second law statement by Kelvin Planck involves heat engines. So you all remember this, that for a heat engine to produce work, it has to exchange heat with two reservoirs. This heat exchange is nothing but heat transfer. So the heat engines need to exchange heat with high and low temperature reservoirs. Now how to exchange this heat? Again, thermodynamics is silent on this, but heat transfer tells us how to exchange heat. So for heat transfer, there must exist a finite temperature difference. However, a finite temperature difference results in irreversibility during heat transfer. So we know that whenever there is irreversibility, there is a underperformance of any device based on the principles of thermodynamics. So this is something we will be. Okay, so I'll stop here and I will continue in the next class. In the next class, that is on Monday, I will complete this particular module theory part and also work out some problems. So all of you come prepared to work out some problems. Bring your notebooks and calculators for the class. Now let me take your attendance. right, let me share my screen so that you can also see. All right, now give me your attendance. Mrutunidhi,
Present, sir.
Abhilash.
Present, sir. Can you hear me?
Yeah.
Sir, present.
Sorry.
Sir, NVC present, sir.
Okay, fine. Okay. Abhilash present, right? Dan Cherian. Madhusudan A.
Yes, sir.
Pranav Dilip.
Present, sir.
Siddharth MV. Srivatsan.
Yes, sir.
Maitreyan.
Present, sir.
Palanivel. Srivatsan.
Sir, Maitreyan present, sir.
Palanivel. Nishant.
Present, sir.
Tamilalagan. Niranjan.
Present, sir.
Vaibhav Karan.
Present, sir.
Abhijit Menon. Kritik Krishna.
Present, sir. Present, sir.
Pranveen.
Present, sir.
Adil Sinju.
Present, sir.
Chaturvedi.
Present, sir.
Chintan.
Present, sir.
Hamza Hassan.
Present, sir.
Ayush Tripathi.
Present, sir.
Harshavardhan.
Yes, sir.
Hemant Kumar.
Present, sir.
Vishwa.
Present, sir.
Chandramouli.
Present, sir.
Vania.
Present, sir.
Sai Rohit.
Present, sir.
T. Raman.
Present, sir.
Vishal AV.
Yes, sir.
Deepesh.
Present, sir.
Anirudh Venkat.
Yes, sir.
Kumaran.
Present, sir.
Sundar Krishna.
Present, sir. Present, sir.
Kunti.
Present, sir.
Niket.
Present, sir.
Narayanan. Badri Narayanan. Avito.
Present, sir.
Ajit.
Present, sir.
Harish Raghav.
Present, sir.
Rahul. Firoz.
Present, sir.
Nihar Aniruddha.
Present, sir.
Vishnukar.
Present, sir.
Gauri Shankar.
Present, sir.
Motishwar.
Chat box.
Prakash.
Yes, sir.
Pooja.
Present, sir.
Prem Kumar.
Yes, sir.
Charan Sarvesh.
Present, sir.
And Ajay.
Present, sir.
Called Simon.
Yes, sir.
No.
Present, sir.
Present, sir.
Yeah.
Present, sir.
Kiran Dev.
Yes, sir.
Arun.
Present, sir.
Al Rao.
Kunal, present, sir.
Okay. Madhukumar.
Present, sir.
Vedant Madhav. Vishwanand.
Present, sir.
Shivani. Riya Vasan.
Present, sir.
Kalai Priyan.
Present, sir.
Shankar Narayanan. Anish. Santosh Raj.
Yes, sir.
Keshav Kumar,
Present, sir.
Ash Kumar,
Present, sir.
Karthik Prasanna,
Present, sir.
Sai Kaustab,
Present, sir.
Arun Ahalyan,
Present, sir.
Sarvesh Krishnan,
Present, sir.
Elsie Femina,
Present, sir.
Jafet Gionel,
Present, sir.
Amal Manoj.
Present, sir.
Okay, I'll call the absentees only. Dan Cherian, Siddharth MV, Palanivel, Tamilalagan,
Present, sir.
present. Huh?
Yes, sir.
Abhijit Menon,
Present, sir. Present, sir.
Badri Narayanan, Rahul, K. Rahul, Vedant Madhur,
Present, sir.
Shivani, Shankar Narayanan,
Present, sir.
Anish. All right. So I've taken the class. You can leave the class. We'll meet again on Monday. As I said, I'll solve problems on Monday. So bring your calculators.
Yes, thank you, sir.
Thank you, sir. Thank you, sir.
Thank you.
Excuse me, sir.
Martin
Excuse me.
Menon. One second. Abhijit Menon, what is your number? All right. Yeah, tell me what you are saying. You're saying something.
Sir, is there any data available on conductivity of plasma?
I'm not aware, but I'm sure it will be available in literature. I don't not necessarily in the regular textbooks, but you will have to look in the research literature.
Okay, sir.
I am not aware personally.
Okay, sir.